The Haber process is a reversible exothermic reaction that produces ammonia by combining nitrogen from the atmosphere with hydrogen derived from natural gas. The process of creating ammonia is based off of this simple reaction. However, the physical process can look a bit overwhelming. Ultimately, though, the operation can be explained using correlations between Gibbs free energy and temperature, as well as relations between fugacity and equilibrium constants, all concepts fundamental to thermodynamics too. Using the Gibbs equation, we can investigate the possibility that ammonia can be produced from this process, where delta G naught of reaction is the Gibbs free energy change with reactants in their standard states as a function of temperature, and delta H naught of reaction at 298 degrees Kelvin is the standard enthalpy change for the reaction at this temperature. The equation and corresponding figure show the relation between the change of Gibbs free energy, the change in enthalpy, and the change in entropy with temperature, all of which are values that have been determined experimentally. The change in Gibbs free energy indicates the extent of the reaction, and since the forward reaction is exothermic, we can see that the products are favored at a lower temperature, and as temperature increases, the extent of the reaction becomes small and the equation shifts to the left, favoring reactants. Calculating the extent of the reaction can be obtained from the properties of the equilibrium constant K. The mole percent of ammonia can be calculated from the mole fraction of ammonia, which is obtained from the mole fraction equilibrium constant Kx given by this equation. The mole fraction equilibrium constant is then obtained from the thermodynamic equilibrium constant through the following relationship. And the fugacity coefficient ratio can be written as well. The fugacity coefficient ratio J can be estimated by assuming that the Lewis-Randall rule applies, at least approximately, for the mixture, so that each component has the same fugacity coefficient that it would have if it were a pure gas at the same total pressure. The principle of corresponding states can then be used to compare the fugacity coefficients of three components. A correlation diagram can confirm that at this reduced temperature, the fugacity coefficient is equal to 1, indicating that J, the fugacity coefficient ratio, is 1 as well. We end up with the following circled equation, and Kx can be calculated from K using experimental values for pressure. From here, a value for the mole percent of formation of ammonia can be done using statistical thermodynamic calculations. There were two major contributors to this process in the 20th century, Fritz Haber and Walther Nernst. Both scientists explored the reaction using high pressures. However, Nernst used high temperatures as well, where Haber focused on lower temperature operations. Haber's largest concern was whether an apparatus could be constructed to synthesize ammonia at high temperatures and pressures on a large scale. Today, ammonia is routinely synthesized by the Haber process. Pressures of 300 to 500 bar and temperatures of 700 to 800 Kelvin are used. A mixture of nitrogen and hydrogen is compressed and then put into the reaction vessel, where it is heated over the catalyst. The reaction occurs to produce an equilibrium amount of ammonia. The equilibrium mixture then leaves the reaction vessel and is cooled so that the ammonia condenses to liquid and is removed. The remaining nitrogen and hydrogen is then returned to the reaction mixture. The final result is essentially a complete conversion of the hydrogen and nitrogen gaseous mixture into ammonia.